she loves playing with loops, both in R and in music. And she has a looper to layer her voice, and the looper's name is Lupita. So, everyone, please welcome Mayarí.
Today, I will tell you about my experience doing analysis to study the impact of a program for refugee children using tools in R. Before I get started, I'd like to mention that this analysis has been done in collaboration with some really wonderful colleagues, mentors, and overall compassionate and ethical humans: Jennifer Hill, Larry Aber, Carly Tops, and Kalina Gicali. I'll start by giving you some background about the project that we were involved in, so that you can have a little bit of context about our research question and about the methods that we use. Since 2011, about 6.6 million Syrians have fled to nearby countries because of violent conflict. At least 855,000 of them are living as refugees in Lebanon. 90% of the Syrian refugees who live in Lebanon live on less than $3 a day. And around 500,000 of them are estimated to be children and youth. So under these circumstances, it's obviously difficult for refugee children to have access to school and to a normal academic development. And those who do get access to public school face different challenges than the local children, like language differences, different grade placement because of previous school interruptions, and also cultural tensions with the host communities. So some of the efforts of the global community involve after-school remedial programs that take into account the realities of Syrian refugee kids. The International Rescue Committee created a partnership with NYU to implement and to study a remedial support program for Syrian refugees in Lebanon. The remedial program is called Healing Classrooms, and on top of their academic development, it targets the children's psychosocial recovery, and it does it with awareness of the impact that violence and displacement have in their lives. The original study design involved randomizing refugee sites to receive access to the Healing Classroom. And the data was collected at the start, in the middle, and at the end of the program. But being randomized to receive access is not the same thing as receiving the actual substance of the program. Among the children that were offered access to the Healing Classroom, attendance ranged from 0 to 80 days, and it was all over the place. So hopefully you can already imagine how bucketing everyone who was given access as treated can be a little bit misleading when you're assessing the potential benefits of this type of support. They all got different dosages of the intervention, and some of them are closer in dosage to the control group than they are to their fellow treated. Our goal was to learn what can work for these children's development. So one of our research questions is about the causal relationship between attending the program and the children's reading skills. The sample that we used for this particular question involves around 1,800 Syrian children from 33 refugee sites that were offered access to the Healing Classroom for about 26 weeks. But when we talk about causal relationships, a crucial concept is that of counterfactuals, which basically refers to what would have been if we were able to travel back in time and switch only the amount of exposure that a child got to the program. A perfect randomization would provide us with a good alternative to time travel, but attendance was voluntary, it cannot be randomized and enforced, and those who were able to attend may not face the same circumstances of those who were mostly absent. And when exposure cannot be perfectly randomized, we need stronger assumptions and we need more resourceful methods. So the first assumption that we needed to make in cases like this is that we have measured all the pretreatment covariates that help predict both attendance and the reading outcomes. A second assumption is that we have enough children that are alike across different exposure levels so that we can estimate reasonable counterfactuals. And that is known as having common support. Another assumption is that the level of attendance of any one child should not affect the reading scores of other children. This assumption, by the way, would be necessary even under a perfect randomization. But the thing is, we cannot ensure that children didn't help each other outside the classroom. So we have to recognize the possibility that our estimates may be smaller than the true impact. Lastly, there are parametric assumptions that are implicit in the modeling approach that each researcher decides to select. There is always a tacit belief that the final model we choose is well suited to capture the true relationships between the pretreatment characteristics, the treatment, and the outcome. So BART, or Bayesian additive regression trees, is one modeling approach that is well suited to make counterfactual estimations, which means it's helpful to estimate causal impacts of treatments that cannot be perfectly randomized, like attendance. Like the name suggests, it is a tree-based method, so it naturally accounts for nonlinearities. It limits us from making generalizations from Western-based research to Syrian refugee populations, and it allows us to adjust for a very large number of pretreatment characteristics. BART is a backfitting algorithm that involves a sum of weak learners. It incorporates a Bayesian framework and a regularization prior. And this ensures that each tree contributes only a small part to the overall fit. At the same time, it provides us with good tools to quantify uncertainty. BART can estimate the uncertainty of each counterfactual prediction, and it gives us a framework to assess the presence of common support for causal inference. And also, when compared against other causal inference methods, it has been shown to be among the top performers. There are a few packages in R that can be used to get a BART fit. The ones that I have had experience with are base tree, dbarts, which is written in C++ and it's faster than base tree, and also BART cause, which is a wrapper of dbarts that is already tailored for causal inference. BART cause made our lives easier because it automatically computes the posterior distribution of the specific treatment effect that we want to get. And it also automatically flags the observations that lack common support. But BART cause is currently focused on binary treatment variables only. So for our attendance question, we began by splitting children into a low and a high attendance group based on the median attendance. We fit the model with this binary version of attendance, and we let BART cause flip the treatment assignment. It estimated counterfactuals for each child, and then it computed the posterior distribution of the average treatment effect of moving from low to high levels of attendance. We looked at 4 different reading outcomes, and we found a significant effect on 2 of them of moving from the low attendance group into the high attendance group, but not so much for the other 2. These estimates, by the way, were obtained after addressing the missing data, and they already incorporate the uncertainty brought in by that missing data. With a Bayesian approach, we get a distribution of the treatment effect and not just an estimate point. And on top of that, here I'm showing you how those distributions can vary across different possible scenarios because of the missing data. And the two outcomes that we could not see an effect for are those that were most affected by the missing information, which you can see in the first and last figures of this slide. But what if the missing data wasn't the only reason that we saw different impacts of attendance for those two outcomes? Because, I mean, attendance is not binary in nature. We wondered if there could be more to the story, like could it have increasing or decreasing returns on children's learning? So we dove into the world of continuous treatments. The idea behind it is that we can estimate a counterfactual scenario for different levels of dosage for each person. If we could travel back in time as needed to adjust the dosage level and test how the outcome changes, then we would know how each person responds to different dosage levels. But while we're not time travelers, we can still use BART to estimate those counterfactuals. Once we have estimated the different counterfactual states for each person, then averaging everyone's predictions at each dosage level allowed us to get what is known as the average dosage response function. Notice that this function can be different to a regression-like approach, which would use only the observed states to fit that curve. The causal DRF package in R did a lot of the heavy lifting for us, and it can estimate the dosage response function using BART by calling the base tree package. Our results suggest that 3 of the outcomes have a positive causal relationship with attendance, but the dosage level at which the marginal impact seems to fade is around 40 days of exposure for 2 of the outcomes, but around 20 days for the last outcome. This gave us additional insight of why an impact was not showing up before for this particular outcome, since we were comparing low versus high attendance using the median split, which was 37 days. These results made sense to us considering that this was one of the most advanced reading tasks, and most of the kids started with very low reading scores. And also the intervention only lasted 26 weeks. We also made an effort to assess the proportion of good counterfactuals that we have at each dosage level. But unfortunately, we don't have time to go into the details of common support right now. But if you're interested in knowing more, please just feel free to shoot me an email. But there's still one reading outcome for which we saw no impact at all. And the first thing to point out is that that particular outcome had a significant larger amount of missing data. We decided to do a little bit more digging about that measure, and we realized a few things. In contrast to the other measures, that one was less detailed, and it provides information of full proficiency on different types of reading skills. And it rates students on a very, very blunt 5-point scale. Another thing we realized was that that measure was implemented independently by the IRC, and its data collection did not follow the stricter protocols that were used for the collection of the other measures. And finally, we also consider that there could be some unmeasured causes for not responding that particular assessment, which could induce bias in our impact estimate. A good chunk of our manuscript is actually dedicated to discussing that, just in case you're interested. So some takeaways: don't get too confident just because there was some randomization in your study. Randomization can it can go wrong sometimes, especially with vulnerable populations. And the answers that you can get when looking at a randomized treatment are not always the most meaningful ones, especially if you want to learn about the substance of a program. So think about whether you're making valid comparisons for causal inference, because in social studies, if you ask the tough questions, you will often need additional tools to answer your questions causally. Well, some of the tools in R that I found useful are dBARTs, BART cause, and causal DRF. Understanding the assumptions that you are making and being transparent about them is very important. And also try to recognize the pitfalls of your data. I know it's uncomfortable, but missing data is pretty much unavoidable, especially with vulnerable and migrant populations. So make an effort both to prevent it and to address it. You won't really know just how much it matters unless you actually assess how different your results can be under different scenarios. And missing data can have different implications depending on each outcome and on each research question. How refined or how rough a measure is has important repercussions in its ability to capture moderate impacts. So it's always a good idea to get the input from a psychometrician and from content experts at some point of your project. And lastly, without data quality, your models have nothing to stand on, no matter how fancy they are. So make sure to invest in data collection and data verification protocols, and make sure that they are well suited for the population that you're studying. And that's it. Thank you for listening, and please feel free to shoot me an email if you have any questions.
Welcome to the research world, take a look around. Data that you thought you'd have is nowhere to be found. Here's some messed up ideas, the skip logic crash. A random fire, turn your paper surveys to ash. You have missing data now, what would you prefer? Rely on complex cases and pretend that you want error. Would you like to impute, best avoid being rude? Dosage impact, many features, tons to compute. Social science